So here's the triple beam balance, and notice that it is not zero. We're about to find the mass of a 50-gram mass. Let me just grab a 50-gram mass. Now 50 is in air quotes there, and let's see how well that. There we go. You can see 50 grams right there. So because this is not zeroed particularly well, and I have all of the counterweights here off to the left, I'm going to add a mass. So I happen to have a wrapper from a Girl Scout cookies, and but that puts it way above zero. So I am going to adjust this until I get it zeroed. And this will be the offset that we're going to have to subtract. We are going for perfection right now. And so now the question is that zeroed well enough? And I'm going to say yes, that actually does look relatively lined up. So now I put the mass onto it and figure out what that is. So again, I haven't adjusted these yet. That is the measurement right there of when I do not have the mass on it. I need to subtract that amount. That unit there, that is, looks like it's just shy of 1 gram. Now looking by eye, looks like just shy of 1 gram, so we can get an estimated digit in there. So now I'm going to adjust it. Well, definitely not that much. That's right, it's supposed to be 50 grams, so let's put it somewhere around 50 and see how well that lines up. That's looking pretty well lined up to me right there. And so that back one is on the 50 grams, and this one is just a little bit above 1 gram. And again, you can get an estimated digit there. So there that is. All right, so there is the LabQuest 2. If you'll notice that sampling rate has been changed to 50 samples a second and duration 20 seconds. This angle right here is for the rotary motion sensor. That is this right here. So as I adjust this dial right here, notice that the angle changes. And then the other thing plugged into it is the linear motion sensor. That's something that's used quite a bit, but as I stick my hand in front of it and move it up and down, notice that the position changes. There is the vernier rotary motion sensor. It is on the vertical rod so that this is upright, which is what I'm looking for here. So now I'm going to be measuring some distances and potentially doing some still shots. This is the 3-step pulley, the 3SP as I've abbreviated. From a side view, this is what it looks like, and I'm going to measure the diameter of each of those tiers. The top tier, because of the thickness of the clamps here, or this plastic piece right here, we're having some issues with measuring the thickness here. So what I'm going to do is I'm going to use this piece right here, and we'll measure. What we're going to do is we're going to measure how far, sort of the depth of the groove there, then measure the diameter across this wide spot here and just subtract twice that, because you got one on each side. And so we're going to end up with, so I put that in there. I'm going to come back in just a second. That tiny little bit of metal sticking out is the depth of the groove. And so, and there we go, in order to be able to find it. Let's peel back for just a second here. That is in millimeters. All right, so the width, don't forget we're going to have to subtract the size of the groove from each side. And so but that gives you an idea of how big that is. And then minus the groove size. And now for the biggest tier, again, I did this just in case the grooves aren't quite the same size. And so that's the size of the groove for the large tier. That's this right there, the groove there. And again. And so now we'll pause again. So the outer diameter, and don't forget you'll need to subtract the groove length and to give you an idea of how big that is. I'm now going to put the 3-tier pulley on this, and notice that it is not a perfect circle. Let's see if I can get a white background there. There is a little groove there, so this does go on a particular way. And so now that is on. So now the 3-tier pulley is on. There's pretty much only one way it will go on. This is the ultra pulley swivel mount, and this is the ultra pulley. So we have the ultra pulley swivel mount, and then just screw this in. And so we'll pause it there. We're on part B here. This is the aluminum disc with cork, and we're going to measure the inner and outer diameter. So measuring the inner diameter, we're using another part of the vernier caliper, and from that we get the measurement. Now we'll set up for the outer diameter. All right, so when measuring the outer diameter, the calipers are not quite long enough for me to just do it from the side like I did for the 3 tiers. So I just make sure when I'm overhead that it is going across the diameter. And so that would be the outer diameter of the aluminum disc with cork. Now to find the mass, don't forget we do have that offset, so I am going to remove the 50-gram mass and put this right here so that I can find it easily again because I already found the mass of it. And now we put this on here and we find the mass of the aluminum disc with cork. That's looking up as lined up as I'm going to get it. So we have the back one is on 0, the middle one's on 100, and this one is right there. And trying to do it without parallax. And there it is. So that's the mass of the aluminum disc with cork. That is the short screw with which we will attach the aluminum disc. So I'm now going to screw that in. So I have it centered as best I can, just to give a little bit of a sense. If it is indeed centered, there shouldn't be much wobble there, as long as I'm holding it still. A little bit, it's not perfectly centered. I'm going to see if I can do slightly better. All right, so I've tried to center it a little bit better, and I think part of that wobble is my hand. So all we have to do is look at a part of it here. And it's looking like not a whole lot of wobble there. So I'm going to call that close enough. All right, this is the steel disc, the one with the big hole in the middle, and we are ultimately going to drop it on top of the one with the cork. But we need to do some measurements now. All right, so taking advantage of this part of the caliper again, getting the inner diameter, and then pull it out and try to get it to focus. It's having issues. All right, I'll take a picture. And then the outer diameter, get that set up for, and that is the outer diameter of the steel disc. In case I have it in there, steel is iron and carbon. And so iron has a symbol of Fe and carbon is C. So I think a number of places I do a subscript of FeC for iron and carbon combination, should be a lowercase e. So just so you know, that's what the FeC is. So finding the mass of the steel disc, and so I'm starting this now, but I'm eventually going to stop it. So it's between 2 and 300. All right, I'm going to pause it here while I get it. That is looking lined up to me. And so the back one is on 70, the middle one is on 200, and this one, let's get that lined up as best we can. And that is the mass of the steel disc. So I spun the aluminum disc by hand and did a recording right there on the LabQuest 2. I care about the I care about the one that deals with angle. So that would be this one right here. I care about the one that deals with angle. And so I'm now going to Kerf It that to get a sense of what the acceleration is. So I'm going to clean this up and we will come back. So that is a cleaned up version of it. This first part out here is before I put my hand on it and then I spun it. So I don't want this part right here for my Kerf It, and I don't want early on when my hand was touching it. I touched it for a very brief time. So I want to do the Kerf It for down here. And so it was spinning long after I stopped recording. And so then we'll do analyze and I will come back. All right, so with this is the quadratic fit for the curve. We have a negative angle and a negative angular displacement. It's becoming more negative. And we have a positive, and don't forget, this is half the angular acceleration. But we have a positive angular acceleration that'll end up being twice that number right there. And, not a bad RMSE. We're now going to repeat the previous experiment, except we're going to put the steel disc on it. And I want that to be centered. That's looking pretty darn close. I'm going to center it and spin it. I think you know the drill here. A little bit of a wobble. So I'm going to pause this while I get that set. So now I'm going to spin this by hand and then record. All right, there's the angle versus time. And so now we're going to Kerf It, and I Kerf It by doing analyze, Kerf It, angle. I want to do a quadratic fit. And maybe we'll get it right. Oh, I did get quadratic fit. And there are the values. So lower RMSE we got going. That's nice. And again, we have negative angles just because I spun it in the negative direction. And then we have an indication of a positive acceleration. Remember that the actual angular acceleration is twice that number right there. And there we go. So I have it wrapped around the bottom tier here. This is the widest of the tiers. I do have it tight right there as an anchor, but in terms of the radius, it's going to be right there. I've got there's a little notch in the tier that's threaded through. I did try it once before that I did not film, and it became unthreaded because it wasn't really tied down. And the other thing that I've done is that I've adjusted the pulley so that when the string goes from to the tier onto the pulley, it should be parallel, so that should be at the same level as that. And then I also have it set up so that it is coming off straight off that. So if we follow the line of the pulley, it should go straight to the edge right there. Note that I did have to pull the aluminum disc off in order to get the tier set up with the string, but the aluminum disc is now back on, and now I'm getting ready to actually do the experiment. All right, so this is a replay of what I had done. I basically had the mass hanging off the end there, hanging on the pulleys, and with the aluminum disc there. And basically, I am going to recreate what I did, but I can't do the actual experiment and film at the same time because I'm doing this by myself. I just can't let go of this film and protect the motion sensor from harm. So what I ended up doing is I jerked the motion sensor out of the way instead of stopping the mass from falling, just because of limited number of hands. But in essence, this is what I had, the aluminum disc sitting right there, and then I let go and the mass fell. And that's the experiment. And I recorded that on the LabQuest, and so now I'm going to go to that data. All right, I'm confirming that that the rate and the duration did not change, so there's still 50 samples per second. And then if I go over to the graph page, I've already zoomed in on the part where that matters. This is the part where I basically jerked it out of the way, so that's garbage. And this is before I let go, so this is the part right here where it is getting closer to the origin and getting faster as it goes. So that's the part that I want to analyze. So analyze Kerf It position, and I want to do a quadratic fit. And so that is the quadratic fit there. It is moving in the negative direction. And because it's moving in the negative direction, the velocity is negative, acceleration is negative, and so therefore it is speeding up as it goes. But anyway, there is the fit. It is curve fitting between the two brackets right there, and I should have the exact same for the angle as well. So let's cancel that, and then graph, show graph 2. And that's the part that I care about. Analyze. Let's actually zoom in. Oh, that's some nice looking data right there. Analyze Kerf It angle and quadratic fit. And there's the information for the quadratic fit. We're going to repeat the same thing again, except this time we'll put the steel disc on top. And I think that's clear enough for you to be able to pull the information off the video. All right, so there we have for the position versus time. And again, my position is going from a larger to a smaller number. So my velocity would be negative, and velocity is negative, and acceleration is negative. Again, that is not acceleration itself. That is half the acceleration. So the fact that velocity and the acceleration will also be negative means it's speeding up. So now I'm going to take a look at the angle and see what we get. So that is the angle versus time, and again did a quadratic fit here. It's looking all scrunched up here just because the thing kept going long after I actually hit stop, or after I stopped the trial. So there's a lot more information that just got scrunched up. But this is the part that we care about. It doesn't undergo that big of a change in angle during the small duration of the trial. There is half my acceleration right there. And again, it's negative. The slope of that is negative, indicating the angular velocity is negative. Angular acceleration will be negative, twice that number, but negative. And therefore it is speeding up as it goes, and that's what we would expect. What's going to happen is I'm going to spin the aluminum disc by hand and then drop the steel disc on top of it, hopefully centered. I'm not placing it, I'm dropping it down onto it, and hopefully conservation of angular momentum will be demonstrated. So that's the basic gist of it. The linear motion sensor is now sort of irrelevant, and hopefully I've disconnected the right one. I did. So the linear motion sensor is now irrelevant, so that is now disconnected. I'm going to make sure I'm still recording 50 samples a second here, and still 50 samples, and still 50 samples a second for 20 seconds. And so again, limited number of hands, so I'm going to do this off screen and come back. I ran this trial about 5 times trying to get that steel disc as centered as I can. It is a little bit off center there, but that is really as best as I was able to do. That's the best one yet. I probably could keep doing it another 10 times, but I don't think it's going to have that significant effect. So next step is look at the data. Looking at the data, notice that I started the recording and then I spun the disc. So that is before I started spinning the disc. My hand was touching it for the first part there. Not that you can tell necessarily, but there's clearly a kink in the graph right here. This is the point in which the steel disc drops onto it. So let's take a look at the velocity versus time. That's angular velocity. And we have a very clear difference. This is the point when the steel disc lands on it. And because we have a much greater moment of inertia, we should have a much smaller angular velocity. I need to know the time. So that time right there is 7 point, let's see, is that the last one? Yep. So 7.06 seconds is the time just before the steel disc lands on it. And then it goes through this transition period. And that's the point at which it reaches a transition period, which is 7.18 seconds. And so it took, if I remember correctly, it takes basically 0.12 seconds for it to reach the new situation. And we want the time halfway in between, the 7.06 and 7.18 seconds. And now we need to do a Kerf It. So we're going to do a Kerf It before the 7.06, that's when the interaction starts, and after the 7.18. And so now let's go back over to angle. And so sometime before then, so that probably is good right there. Let me start on this end though, actually, so that I know I don't go too far. All right, so I'm doing the plot up to 7.76 seconds. That should be fine. Analyze, Kerf It, angle, quadratic. It is curve fitting to the brackets right there. This is before the collision. So that's the information before the collision. And so now we're going to do after the collision. So cancel. And then afterwards, it has to be after 7.108. And when we start at this end, so that that's up to 7.4. So I clearly did not get into the range of the interaction. And analyze, Kerf It, angle, and quadratic. And what we're going to do is, there's the information for afterwards. What we're going to do is take a look at, well, project backwards. We have the information from, sorry about the shaking. From this, we have enough information that we should be able to work backwards until we figure out how fast it was going at that midpoint. And we can look at the angular velocity this way, angular velocity that way, figure out the angular momentum, and no doubt it will work perfectly because that's the way physics labs do. And I think that's it for all the data collection. At this point, it's a matter of number crunching. Woohoo! And don't forget, I haven't said this in a lot of the other videos, but don't forget, rejoice. This is physics. No, I'm not recording now. No. What you need? Oh. No, I hadn't forgotten about him. Yeah. No. As soon as I finished doing this video, I was going to help you bury him. You know. All right, I'm just going to post this very quickly, and then we'll bury the salesman. Okay.